A sequence is a particular kind of function whose domain is the set of whole numbers. And just so that there's no confusion, we'll say that this is the set of all positive integers. We're going to begin that with 1. So we're going to go 1, 2, 3, and so on. So we don't include 0. That's why we specified this with all positive integers. The independent variable is not going to be x like what we're used to. We're used to functions in terms of x. In the sequence case, we're going to let the independent variable be the variable n. A sequence is represented by listing the values of this particular function in order. These are known as the terms of the sequence. Okay, so this list goes on forever. It never has a stopping point. You can assume it goes to infinity. So you're going to have an infinite number of terms in any given sequence. The a(n) is representing the nth term. So the value a sub n is whatever the value is of the nth term. And then the set of all of the a(n)s is the entire sequence. So let me show you an example of what we might be talking about. Suppose you have a sequence and the terms are 1, 3, 5, 7, 9, and this list goes on forever. And so this is the list of odd integers, where the first odd integer listed in the sequence is 1. And so therefore a1 would be the value 1, where a2 would be the value 3. And a3, the third term, has the value 5. And the fourth term, a4, has the value 7. And you understand what I'm talking about now when I refer to the a(n)th term. All right, when we put all of the terms of a particular sequence in these fancy brackets here on the sides, that is designating the fact that we have a sequence. And those are all of the terms. The n factorial, this is a quick review for us since we haven't dealt with factorials this semester. The n factorial value, the value of n factorial is equal to n times n minus 1 factorial. So suppose you want to find, here's an example. Suppose you want to find 6 factorial. So 6 factorial, we may recall, is equal to 6 times 5 times 4 times 3 times 2 all the way down to 1. And the product that you get in the end is whatever the 6 factorial is. And so I could have written this as 6 times 5 factorial, because 5 factorial is 5 times 4 times 3 times 2 times 1. And so this is just another way of defining what n factorial looks like, which could be useful when you're defining sequences. Some properties of a sequences I want to draw your attention to are shown here on this page. Be familiar with the particular forms and how to use them. You do not need to memorize these because I've given you, I've given you a formula sheet, which was on the other side of the Chapter 9 formulas. Chapter 9 was the formulas we looked at for conic sections. It was a 2-page document. The second page listed a lot of formulas for Chapter 11. And so the formulas that you're going to be seeing in Chapter 11 are lesser known, less commonly used formulas. And so therefore, even in a regular face-to-face class setting, I would allow you to use these formulas on a test. So you might want to get that sheet printed out so that you've got that handy for when you do the test over this material in the final exam as well. But some of the properties that we're going to see here, we'll go ahead and show some examples, but if a(n) and b(n) are two separate sequences, and c, the value c is just some real number. It could be positive, negative, rational, irrational, decimals, fractions, does not matter. And so c is a number, and a(n) and b(n) are two separate sequences or lists of terms, okay? Lists of numbers. You can write the sum, this capital sigma that you see there, that is the summation sign right there. So that means add them up, okay? So capital sigma means add them all together. And so if you have this value c times the sequence a, and I'm changing the letter to a k, which you'll see why shortly. But if you have a number times the sequence, you can bring that number c into the front of your summation and then add up the terms individually. And at the very end, multiply your sum by your constant. In other words, you can multiply each term value times the constant and then add all of that together, or you can add all of the term values and then at the very end multiply by that constant c. And that's the idea. Okay, that constant c will not affect your sum if you do it first or if you do it at the end. The next formula is going to show you that if you're adding two different sequences together, your AK and your BK, or maybe you're subtracting these two sequences term by term, you can treat that as two separate summations. Work out all of the A terms and then work out all of the B terms, and then either add or subtract them as needed. The next formula shows you that, once again, C is a constant, right? C is a constant. You would make a note of that. So it's just a number. If you're adding up the same number lots of times, there it is, C plus C plus C plus all the way down to here at the end. If you keep adding that number a certain number of times, maybe n times, that's what n is. If you added it up n times, then you can just figure out what that C value times n would be, and that would be the same exact sum. Okay, so some new notation that we just got introduced to. This is now the sum, and you're told where to start, and you're told where to end. So you're going to start it at 1. That's the first term. And you're going to then, the next term would be the second term. The term after that would be the third term, and so on and so forth, until you get to whatever the nth term is. And in this case, you would be told where to stop. So you might do this for, 5 times, 5 terms, or 10 terms, or 100 terms. And so that would be the ending value of n. All right, the next formula is where you're not adding up a constant that's the same each time, but this constant is changing. And so this constant is now called k, and this is why earlier I changed the n into a k. And I said you'll see why shortly. Okay, so you're adding up some variable, some counter variable k. And now what's going on here is this value k is going to be changing. So the first iteration through the sequence to get that first term, right, this is where we start, is just going to be the value 1. And so you replace the variable k with that counter number. The first count off number is 1. The next iteration, you go to the next integer value, which is a 2. So we started at 1. The next term is going to be a 2. The third term is a 3, and so on and so forth, all the way down to whatever the last term is told to be, the nth value. That's where you end. And so if you add up all of these digits, 1, 2, 3, 4, 5, all the way down to where you're told to stop, the formula that you could utilize to get that same exact sum is n times n plus 1 over 2. And in the classroom, I like to prove that, but I don't think we're going to do that this time. All right, the next formula is if you're adding up k squared so many times, n times. The first time through, it's going to be 1 squared. So I didn't write out the terms this time, I just gave you the formula, but I'll show you what the formula is counting up. It's counting 1 squared plus 2 squared plus 3 squared plus 4 squared. So each successive iteration is going to be one integer value that's bigger than where you were. Okay, so you just keep increasing the integer values by 1. And then this last formula, you're probably getting the idea now. You're adding up k cubed. The formula is given to you there. So in order to use the formula, you have to know what the ending value n is in your sequence. How many terms did you do this to? And that is what you're going to put in for the value of n. All right, here's an example. Write down the first 5 terms of the sequence called d. d sub n is represented by the sequence you see in the brackets. And so the first 5 terms tells you that you want to start with the first term, then the second, third, fourth, and fifth. So D1 is representing the first term's value. And so you just replace the letter n with the value 1. So I'll write it all out. So it's negative 1 to the exponent 1 minus 1 times, now n is 1, remember, 1 divided by 2 times 1 minus 1. So you've substituted the value 1 in place of the n's up here in your expression. Here and here and here. All of that became a 1. And you're going to work it out. So negative 1 to the 0 power is 1 times 1 over, and then 2 minus 1 equals 1. and the ending result is 1. That's the first term, that's D1. D2 is where you substitute the value 2 in place of all of the n's that I tried to highlight in green. And so you're going to substitute 2 here, 2 minus 1, times now 2 divided by 2 times 2 minus 1. Okay, and you're going to get negative 1 to the first power times 2 divided by 3, which is negative 2/3.